Welcome back, student. We're making our way through Unit 1, Limits and Continuity, and today we're going to be talking about limits to infinity. This is something you may have seen in your pre-calc course. It's often been called, I'll write it here, end behavior. Because when we were in pre-calc, you may or may not have been talking about limits to infinity. And so we like to use the term end behavior. What happens at the ends of a function? As the x values get really, really big or really, really negative. I don't like to say really, really small, but really far from zero. So in the negative infinity direction, what's happening? So if we look at these functions, on the left, we have negative 1/2 x minus 1. This is just a line. We have 1/2 x minus 1. And as x gets bigger and bigger and bigger, if we were to plug in infinity, we go towards infinity. We just keep increasing in the positive direction. The same in the negative direction. We'll just go towards negative infinity. And I actually want to go down first. If we go to x cubed minus 4x, if we plug in a really, really big number, that is going to go towards infinity. And if we plug in a really small, really, really negative number, rather, we're going to be going towards negative infinity. So these two functions have odd degree. They're polynomials with odd degree. That means as we plug in big values for x, this first term is going to get really, really big faster than any other term. So if we had, if we were to add x squared to this, for example, x cubed is going to get bigger so much faster than the x squared term that even if we subtract this, let's say not plus x squared, but let's say minus 100 x squared. If we plug in infinity times negative 100 is very big, but it's still not as big as infinity times infinity times infinity. So that's why we just need to look at the highest degree term. Usually that'll be the first term. So with the highest degree term, if we plug in a really big positive number, when it's odd, it will go to a really big positive value. If the degree is odd and we plug in a really, really big negative number, when we cube a negative number, we still have a negative number. So this would go towards negative infinity. Same thing here. But what about even degree functions? So we have y equals negative x. When we plug in infinity, infinity squared would be really, really big, but because of the negative sign in front, we'll go towards negative infinity. When we plug in negative infinity, when we square it, it will become positive infinity and go toward, but because of the negative sign in front, we'll go towards negative infinity. And I haven't been writing these limits, but let's just go ahead. Let's go ahead and do that. The limit as x goes into infinity of f of x is infinity. Limit as x goes to negative infinity of f of x is negative infinity. Both of these are negative infinity, rather. Okay, and looking at the next one, this is of even degree as well, because we're just looking at the largest degree. So the limit as x goes to infinity of f of x, this term will get bigger much faster than the rest of the terms. And when we take it to the fourth power, it will always be positive. So this limit will be positive infinity. Same thing with x going to negative infinity. Okay, this is infinity. Okay, now our last two examples here, because we're going to get into some problems that will use these. If we plug in infinity here, if we do the limit as x goes to infinity of 2 to the x, let's call this g of x, this just keeps getting bigger and bigger and bigger. 2 to the infinite power is a huge number. And we can see that graphically. We can see it just keeps going up. Now, as we take the limit as x goes to negative infinity of g of x, what's happening here? Well, it's going down, our graph is going down, but it's not going below the x-axis. Why is that? Well, the reason is we have 2 to the x. When this goes to the negative infinity power, this is the same as writing 1 over 2 to the infinity, or 1 over infinity. And 1 over infinity would be 0. When we take one thing and divide it into an infinite amount of pieces, those pieces are so small that we just consider them to be equal to 0. So the limit as x goes to negative infinity here would just be 0. So that's something to be conscious of with the exponential functions. Looking here, negative e to the negative x, we run into the same kind of situation. We have x goes to infinity of h of x, limit as x goes to negative infinity of h of x. Okay, when we plug in infinity, we have negative e to the negative infinity. So this one, I'll use blue. This limit would be equal to 1 over negative 1 over e to the infinity, because e to the negative infinity is 1 over e to the infinity. This ends up being negative 1 over infinity. Negative 1 over infinity, once again, doesn't matter that it's negative. Anything divided by infinity will be essentially 0, so we'll say this is just 0. We're going towards 0 here. Okay, and as we go towards negative infinity, we have negative e to the negative infinity, which is negative e to the infinity. E to the infinity is infinity, negative infinity is our answer. So as we go towards negative infinity, the limit of h of x here would be negative infinity. Okay, so those are functions that are not rational. They're strictly polynomial or exponential functions. Now we're going to be looking at rational functions with infinite limits. This is the most common type of infinite limit that you're going to be given as a problem on the AP exam. So what is a rational function? It's basically one polynomial or exponential function divided by another. So what you see here, we have ax to the m plus cx to the m minus 1 plus dot 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 plus c. I know this doesn't look very nice. All I'm saying is that the largest power is the first term. So the degree is the m degree, and then everything else is a little bit smaller. So for example, we could have 8x to the 8th plus 7x to the 7th plus 4x to the 3rd. We can skip. We don't have to have every degree after 8, below 8. We can, these coefficients could be 0. And that's fine. That's fine. So this is a perfectly fine rational function for the numerator. In the denominator, we have bx to the nth degree plus dx to the n minus 1. So just smaller once again. So let's say 7x to the 6th plus 5x squared plus 2, for example. So this is just an example of a rational function. Let's talk about 3 different cases we could find. So first is when m is equal to n, when the degree of the numerator is the same as the denominator. So in this example, we're looking at 2x squared plus 3x plus 6 and 4x squared minus 3x minus pi. I just put the pi there to confuse you. So the highest degree in the numerator is the second. In the denominator, it is also 2. It's a degree 2 polynomial. Since these are of the same degree, as we go towards infinity, these 2 terms will go towards infinity the fastest. So we can just pay attention to them as we go towards infinity. So we have 2x squared over 4x squared. Now we can use algebraic manipulation in order to find this limit. So we can cancel the x squareds. And we can also cancel the 2, make this 1, and make this 2. So we have the limit as x goes to infinity of 1 over 2. So this is just equal to 1 over 2. And you may remember from pre-cal that in the situation where m is equal to n, our horizontal asymptote is just a over b. Y equals a over b. And in this specific case, it would be 1/2. So as we go towards infinity, we'll be going towards our horizontal asymptote. So our limit as x goes to infinity and the horizontal asymptote are the same. Okay, we'll continue here in the middle. We have m is less than n, so we pick out the largest degree terms. We have the limit as x goes to infinity of x cubed over 2x to the 4th. We can cancel the x cubed and 3 of the x's in the denominator. So we have the limit as x goes to infinity of 1 over 2x. Okay, and now we can solve this via direct substitution because we have 1 over 2 times infinity, which we've already learned is equal to 0. When we're dividing by 0, or when we're dividing a number by infinity, our limit is equal to 0. And once again, to reference pre-cal, the horizontal asymptote when m is less than n, when the degree of the denominator is larger, we learned was y equals 0. And that's what we found. That's what our infinite limit was. Okay, and finally, when the numerator is bigger than the denominator, we do the same process. We pick out our largest degree terms, take the limits, so x goes to infinity, 5x to the 5th over 4x to the 4th. And we can cancel 4 of those. So we have 5x over 4, limit as x goes to infinity, 5x over 4. If we were to replace x with infinity, we get 5 times infinity over 4, which is simply infinity. So we do not have a horizontal asymptote. And that means as x goes to infinity, our limit goes to infinity. No horizontal asymptote. The limit is equal to infinity. Okay, let's talk about a few more challenging limits to infinity. So we have something with a square root in the numerator and something with an x to the 5/2 in the denominator. What we're going to do here, we're still going to look for our highest degree term. So we have x to the 6 minus 2x plus 5x squared. 5x squared is certainly bigger than 2x, and especially the square root of it. But if we pull out x to the 6th, if we were to take the square root of x to the 6th, it would be x to the 3rd. We actually can do that. We're kind of breaking the rules of math, but we can take this out and pretend like this is negative x to the 3rd. We're taking the square root of x to the 6th and we're bringing it out. Okay, so I've got to write my limit here. The limit as x goes to infinity of negative x to the 3rd. We can only do this when we're doing an infinite limit. We can only disregard the other terms in that case. In the denominator, we have x squared and 5/2. At 5/2 is bigger than x squared, so we have x to the 5/2 here. Okay, great. Now we can do some canceling. So we have x to the 3rd over x to the 5/2, or 2.5. So we can cancel all of these, and we would leave 1/2 up here. So we have the limit as x goes to infinity of negative x to the 1/2. If we plug in infinity here, we have the square root of infinity, which is infinity. But because this is all negative, our limit is negative infinity. Okay, we have 2 more. It's the same problem, but we're going to see the limit as x goes to infinity and the limit as x goes to negative infinity. Okay, as we go towards infinity, we have e to the x minus 4x. We need to think about which of these is going to get bigger faster. So x, it would just be 4 times infinity, which is infinity, but e to the infinite power is actually going to go to infinity faster. We have e times itself an infinite number of times. So we're just going to be looking at this term, and we have the same thing in the denominator. We have 2e to the x going towards infinity faster than x squared. So we can look at this like so. The limit as x goes to infinity of 5e to the x over 2e to the x. And like the last problem, we can just cancel the e to the x's. So the limit as x goes to infinity here is just 5 over 2. Okay, and the last, we have the same problem, but we're going towards negative infinity. Last time, e to the x was going to go towards infinity faster than x, but now when we're going towards negative infinity, we kind of maybe want to rewrite this and think of it as e to the negative infinity, right? Let's just think about what that is. What is e to the negative infinity? That's 1 over e to the infinity, which we talked about is 0. So if we just plugged in negative infinity, this term would go towards 0, whereas x would go to negative infinity. So this term is going to be more powerful when the limit goes to negative infinity. And again, in the denominator, 10x squared is going to be going, if we plugged in negative infinity, that value is going to be much larger than 0, which is what the first term would be. So let's write that out. We have the limit as x goes to negative infinity of negative 4x over 10x squared. We can cancel one of the x's, so we have the limit as x goes to negative infinity of a negative 4 over 10x. When we plug in negative infinity here, we're going to have a negative infinity in the denominator and a negative 4 in the numerator. So this ends up being negative 4 divided by negative infinity ends up being, 0. Just ends up being 0. It doesn't matter if it's positive or negative because the bottom makes this 0. All right, guys, I hope this covered all of your doubts about limits towards infinity. I know this was a bit of a long video, but there was a lot to cover. I'll see you next time.